Great afternoon, everybody. All right, so we're here back and we're going to start on section 5.2. Now, I know last time we ended on a cliffhanger where we were trying to identify what was the answer to the very last question here when we had this contractor that was considering a sale, so on and so forth. And I said, hey, I want you guys to try this, see if you guys can get it. And the answer should have been part A. So if you want to see the answer to part A, you're going to have to go through and you're going to have to ask some questions within the discussion board. That way we can get through those, through that calculation. So now that we got that answer, let's go ahead and start with section 5.2, which is the binomial probability distribution. So when we're dealing with a binomial probability distribution, there's a few things that we have to consider. The few things that we have to consider is, do we have a fixed number of trials? That's the first thing. The second thing is, are those trials independent? All right. The third thing is, can we classify all of the outcomes into two categories? And then finally, is the probability of success, does that remain constant in all of these trials? So that's going to be important, that it must remain constant in all of those trials. Now we have terminology for this. N is going to be the number of fixed trials. P is the probability of success. Q is the probability of failure. X is the specific number of successes in N trials. And we're going to be very, very careful here because the word success here just means that we have a favorable outcome. Favorable outcome just means that we are looking at the outcome occurring, meaning what is the probability that that outcome occurs. And then finally we have P of X. P of X, that is what we're looking at when we're trying to find a probability. All right, so that's P of X. In other words, the probability of getting exactly N successes among those N trials. So let's see if we can dissect all of this on this example down below. So the example here says that according to Wikipedia, 19% of Mexican residents are vegetarians. If we randomly survey 20 Mexican residents, what is the probability 3 of the Mexicans are vegetarians? So fill in the given values with the information presented. So the big question is, what are those two outcomes? Well, the outcomes that we're observing are, can a Mexican resident be vegetarian? Or what's the other possibility? That they're non-vegetarians. So we do have two possible outcomes. So what we have here is we have the third condition met. Awesome. Next, do we have a fixed number of trials? That fixed number of trials is going to be N, which in this case is going to be 20 because we are randomly serving 20 residents. So here we have the first condition met, that we have a fixed number of trials. Now P, do we have a probability of success? And again, success in this case just means that we are looking for the probability that the selection or that the outcome that we're looking for was achieved. And that selection or that probability is this 19%. So when we look at 19% as a probability, that 19% is going to be 0.19. Awesome. Now, probability of failure. Probability of failure, this means that we are looking at some sort of complement. So when we're looking at complements here, we're going to be looking for the case that P plus Q is equal to 1. Therefore, if we have the probability of success, then the probability of failure is just going to be 1 minus Q. All right, so let's see if we can get that, or if we can do this the other way around, that if we want Q, then that's just 1 minus P. Both the first equation leads to both outcomes. All right, first equation leads to both those outcomes. So let's look at Q. If P, probability of success, was 0.19, then Q must be 1 minus 0.19. So you can do the quick math on that to say 1 minus 0.19 should be 0.81. Nice. So now we got the probability of failure. And finally, we need X. X is the number of successes that we are looking at. The number of successes in this particular case is going to be 3. So what's the probability of 3 Mexicans being vegetarians? So now let's see. Are the rest of the 2 conditions met for this example? So condition number 2 says that trials must be independent. So every single trial that we run, well, let's see if they're independent. If we go to one household and we find that the Mexican residents there are vegetarian, does that somehow change the probability of me going to, I don't know, say a house down the street and finding out if those Mexican residents are vegetarian or not? All right, the answer is more than likely no, it's not going to be affected, which means that they are independent. And because they are independent, that means that the probability of success is going to remain constant in all of these trials. All right, so I kind of see number 2 and number 4 kind of being fluid with one another, right? We can use those interchangeably, which is going to be really good. So now that we've extracted all this information from this problem, we can then go through and start seeing how are we going to be applying this probability distribution. Now, there is a formula for this. The formula for the probability distribution is given here. And I'm going to highlight this in yellow. It is important, however, since we're using the TI-84s, it's going to kind of be irrelevant for us, because the TI-84 actually uses the embedded programs. So some programmer, what they did is they took this formula here and they programmed the formula into this specific user face. So what we want to do is we want to keep using that binomial PDF. All right, very, very specific that we're going to use binomial PDF, and we're going to need 3 inputs for that. We're going to need what is N, what is P, and what is X. All right, so let's look at the problem here that says use the problem from above to set up and evaluate using both methods. All right, so we're going to do it using both methods. Now, the first method is just going to be for completeness sake. All right, so I'm going to write on here method 1. And with method 1, we're going to use this formula. P of x is equal to n choose x multiplied by probability raised to the power of x multiplied by q raised to the power of n minus x. So for method 1, we're going to use this example. And for method 2, this is going to be the preferred method. We're going to use binomial CDF, binomial PDF. All right. And again, this is going to be the preferred method here. All right, so let's work with the long method first. All right, so we want the probability of selecting 3 of the Mexicans or Mexican residents that are vegetarian. So probability of 3. N from above was 20, so that's going to be 20 choose 3. That's going to be my first parenthesis, multiplied by the next one, which is p to the power of x. Now, p from the problem above was 0.19, and x was 3, multiplied by q, Q was 0.81, that's a probability of failure, raised to the power of n minus x. So n minus x, that's going to be 20 minus 3. There we go. Now, there's going to be a lot to work on here. So what I'm going to do really quickly is I'm going to switch over to the calculator version, and I'm going to go through and I'm going to start making these substitutions. All right, so here's my calculator. So I'm going to go through really quickly and I'm going to start doing those substitutions. So the first thing I'm going to do, I'm going to put it in exactly as I wrote it. Open parenthesis. The first number was 20. I need the choosing option, that big capital C. The way you find that is you go over to the math button. Once you go to the math button, you need to go over to the probability function. So right now we're under math, so we're going to go tab on the right arrow. That's now it bypass number and then complex, and then we're going to go one more for probability. Here we go. Notice the third one down, number 3, that's the one that says NCR. That's the one that we want to use. So I'm going to go down by 3. Here we go. Or you can simply select the number 3 and it automatically chooses it. Now look at this. It automatically gives me the input that I need. So this is 20, choose 3. Now notice the little right arrow. The little right arrow is still kind of on that subscript of C. I need to get it out of there. So I'm going to tab on the right arrow. Here we go. There we go. Now I'm going to close that parenthesis. Perfect. That's the first input. Multiplied by the next parenthesis, which was 0.19, close parenthesis, raised to the power of 3. Again, it's on the superscript or on that exponent, so I'm going to tab down. So I'm going to use the right arrow for that. Multiplied by Q, which was 0.81, close that parenthesis, raised to the power of, and here you can do 20 minus 3, like this, or if the arithmetic is pretty straightforward, as in 20 minus 3 is 17, then you can naturally just insert the exponent of 17 and everything's fine. As it stands, everything looks good. I'm going to hit enter. Here we are. So the probability of finding that exactly 3 Mexican residents are vegetarians out of the 20 surveyed is going to be 0.2174, so on and so forth. Awesome. Now that we have this part for the calculator, we're going to switch back to the notes and we're going to keep going. All right, so here I'm going to write that probability. This one was approximately 0.217. Now for method 2, we're going to do the exact same process, but now we're going to use the embedded feature. The embedded feature is going to say, again, all we need to know is what is n, what is p, and what is x. So n, according to our work, was 20, p, probability of success, 0.19, and then x was 3 trials. This is all that we need. When you do your take-home exam, you're going to have to show me either method 1 or method 2. If you show me method 2, then this here is what I want to see for method 2. You need to write it out exactly like that before you go through and put it into your calculator. This will let me know that you are going through the process and you're extracting all of the information that is needed. All right, now that we have this, let's go to the calculator. All right, so here we are. Let's go find that binomial PDF. Now, the binomial PDF, the binomial distribution is exactly what it says. It is a distribution. So if you notice, under the little tab arrow, under the little arrow to scroll down, there is this little blue DISTR, that stands for distribution. We need to access that. So what I'm going to do really quickly is I'm going to access it by hitting second and then accessing that distribution. And here we have a list of all of the different distributions that are provided for us that are already done. So we just need to scroll down to find binomial PDF. Notice it's right here on A. So once I find it, I'm going to highlight it. That's binomial PDF. Please make sure that you do not choose CDF. In other words, you do not choose B. We will get to what B does in a few minutes. For now, we want to stick with binomial PDF. Press enter, and it's going to ask for the input that we just wrote down. How many trials? Well, we're looking at 20 trials. What's the probability of success? Our probability of success was 0.19. Great. What's the X value? In other words, how many are we looking to occur? That X value was 3. I'm going to go down, I hit enter, and then it highlights on paste, and I press enter once again. Notice this formula that's on the screen is the exact same formula that we have written down on our paper. We're going to press enter. Notice these two answers right in here, these two answers are identical, which means they give us the exact same answer. So when we start looking at this, it's a preferred method to go with binomial PDF. So binomial PDF, as we saw, gives us the exact same answer, 0.217. And again, it's going to be the preferred method, so my suggestion is start getting used to that method. That way we can keep working with that method more and more quickly. Let's go to the next example. On this next example, it says that we survey 5 PCC students and ask, is this your first year here? Assume that 20% of all PCC students are in their first year. All right, awesome. So let's go through the task of trying to see if this is a binomial distribution. So do we have a fixed number of trials? Fixed number of trials, yes or no? Yes, that's n is equal to 5. Awesome. So fixed number of trials, great. Condition 1 met. Are the trials independent? Meaning that if you catch one student and you ask that one student, hey, are you a first year here? Does that affect you asking, I don't know, your classmate or the person enrolled in your PE course? No, it should not affect that, which means the trials are independent. Number 3, each trial must have outcomes in 2 categories. So what are the responses here? The response is yes, they are first year, or no, they're not a first year. So the responses are classified into 2 outcomes. So does the probability remain constant at all times? Yes, it does. The probability that we are using, we're running under the assumption that 20% of all PCC students are in their first year. So that probability does not change at all, which means all of the conditions are satisfied for a binomial distribution. With that being said, let's see if we can find Q. Remember, Q is the complement of P, which means Q must be 0.80. Awesome. And we want to find it just for consistency's sake. If we need it, great, we have it. If we don't need it, okay, awesome. Then we won't need it. So let's start answering the first question. The first question is, what is the probability that all 5 students are new? So the probability that all 5 students are going to be new. Now again, you can do this using your preferred method, or you can do it using the probability method that we saw before. All right, notice they're all independent, so these are all independent trials. Finding the probability that they are all 5 new students, wouldn't that just mean that this is just a probability remains constant at all times? In other words, 0.20. to the power of 5 because, again, we're running 5 trials. Do this on your calculator and you will get that the probability is approximately 0.00032. Now, some of you might say, well, Mr. Castro, you said that we wanted to use a preferred method. Why aren't we using the preferred method here? Now, you're absolutely correct. We can use a preferred method. Let's see if the preferred method actually gets us the exact same answer. We're going to work with binomial PDF. N, what is N? That's 5. What is P? P was 0.20. And what was X? X was 5. Great. Now we're going to go to the calculator. All right, so on the calculator, we're going to go to the binomial distribution. So again, to access that distribution, you're going to press second, VARS. Here we go. Now go downward. And remember, we got to go all the way down to the letter A for that binomial PDF. Hit enter. Enter the trials. There was only 5 trials. Probability of success was 0.20. X value, we want to select all 5. Paste that. Here we go. It's exactly as we wrote it out. Now press enter. Notice the calculator gives me the exact same answer. And some of you might be saying, whoa, Mr. Castro, 3.2 e to the power of -4, that's not the same answer. Well, we got to take it back a bit. It is, in fact, the exact same answer. And I'm going to show you why in just a bit. All right, we're going to go back to the notes so I can write down a few things. All right, here we are. So the answer that the calculator gave us, I'm going to scroll down right over here. Hey, look at that tree diagram. Awesome. So when the calculator gives us 3.2 E, and then it says -4, what this says, this is 3.2 times 10 to the power of -4. 10 to the power of -4. All right, that's going to tell us that we're going to take this decimal place, take that decimal place, and we're going to move that decimal place to the left. And we're going to move it to the left 4 times. There we are. So this naturally says we get 0.00032 because, again, we move this 1, 2, 3, oh, excuse me, 1, 2, excuse me, 1, 2, 3, 4 times to the left, which means we got the same answer. All right, so we see that it gives the exact same value. Now, this is going to be very, very important because, again, when we're looking at really small probabilities, and again, this is a really small number. When we're looking at really small probabilities, the TI-84 will automatically default to scientific notation. All right, that's what this is called. This is called scientific notation. Now, that scientific notation, your answers in my class should never, ever be in that form. All of the answers that I want to see in my class must be in decimal form like this. All right. So if you ever have any questions, again, please feel free to ask. So the next question, part B. Here we go. Part B. What is the probability that 2 or 3 students will be new? So again, we're using that OR probability. Now remember we said that there was keywords? That keyword here is OR. So we now have to default back to chapter 4. When we were looking at chapter 4, we were looking at probabilities that were involving the statements and an OR. So at this point in time, we want the probability of 2 or 3. Now the big question here is, are the events mutually exclusive? Does one affect the other? If 2 are selected, does that affect that 3 will be selected, that they are new? Right? The probability here is mutually exclusive, which means when we do the subtraction of 2 and 3, that subtraction will automatically go to 0 because they are mutually exclusive. So, here we go. Let's do this using probabilities. We're going to do the binomial PDF. N was 5, P was 0.2, X is 2 for the first part, plus the same process again, binomial PDF, and this time 5, 0.2, comma 3. Now I'm going to highlight here to see where these are coming from. The first binomial probability comes from P of 2. The second binomial probability, P of 3, is this probability here. So I'm going to go to the calculator and I'm going to start inserting those probabilities exactly as I see them. All right, here we are. Let's go to that binomial PDF. So again, second distribution, go down all the way to A. If you don't want to go down, scroll down all the way, you can also scroll up. Scrolling up takes you to the bottom of the list, and you'll see it takes us about the exact same amount to get here to binomial PDF. Once you find it, press enter. Great. So we got binomial PDF, we got 5 trials, probability of success is 20. The X value for the first one was 2. So I changed that to a 2. I paste it. There we are. I'm not going to hit enter. Instead, I'm going to press plus, because I want to take this probability and add it to the next one. So I'm going to go through the exact same process now. Second distribution. Here we are. We're going to go to binomial PDF. Here's another trick. You don't want to scroll, but you know where it's at. Remember, it was in list A or category A. So I'm going to hit alpha A. There we are. Binomial PDF automatically. 5, success was 0.2, and this time 3 trials. Ooh. There we go. This time 3 trials. Paste that. Perfect. Now if you see that line now says, hey, I'm adding these 2 binomial probabilities together. Let's see what we get. Let's press enter, and we get 0.256. That is amazing. All right, let's go back. All right, so now that we found this, we're going to say, hey, all of this was equal to 0.256. Great. Let's look at part C. Part C then says, what is the probability that at least one student will be new? So at least one. Now remember back to the rule of complements. At least one. What's the probability of at least one? Well, that was 1 minus the probability of none. In this case, probability of none is probability of 0. But using the binomial formula, or the binomial PDF, this is going to be 1 minus the binomial PDF, 5 trials, probability of success was 0.20, and this time the X is that we want none to be selected, that they are new students. All right, let's go ahead and put this into the calculator. Here we go. 1 minus, I need the binomial, here we go. I want binomial PDF, 5 trials, probability of success. However, this was no selection. Here we are. So this entry looks exactly as I wrote it. Press enter, and we get this probability, 0.67232. So I'm going to write that probability down here. 0.672. Nice. Now, part D, we want to create a probability distribution for this exercise. So probability distribution. Again, we need to identify what is n, what is p, and what is x. So for this, we're going to have a nice little trick. So we are going to have a nice little trick for this one. And in order to do that nice little trick, we need the calculator. Now, we want to fill in these probabilities with these associated corresponding variables. X is 0, x is 0, x is 1, x is 2, x is 3, x is 4, and finally x is 5. And these x variables represent the number of students that are selected within that survey. So if we select 5 students, could we have a probability that none of them are first years? Yeah. Could we have a probability where only 1 out of the 5 is a first year? Sure. Could we have where 2 of them are first years out of the 5? Yeah. So on and so forth, all the way till we get to 5. If we accidentally or if we coincidentally select 5 students out of the 5 that we surveyed that are first years, well, then we hit the probability on the head. So let's go through and let's see if we can figure out what these probabilities are without doing so much work. So what I want to do here is I want to access the binomial distribution. So I'm going to go through and I'm going to access that binomial distribution. All right, so again, second distribution, I want binomial. So scroll down all the way to A, or again, you can hit alpha, A. Here we are. 5 trials. Probability of success was 0.20. This time we're going to leave our X value empty. So if you have a number there, just press delete. Don't press clear, just press delete. Once you do that, just hit enter all the way you go to paste. There we are. What you're telling the calculator to do now is to generate all of the probabilities that are given by this distribution where we have 5 trials and the probability of success is 0.20. Hit enter. It should provide you with a list. This is a first number, 0.32768. Next number is 0.4096. Next one is 0.2048. And if you tab on over to the right, you're going to be able to see all of the ones that follow. And keep going all the way to the last one, 3.2 e to the negative 4. Remember, that scientific notation, we don't want it in scientific notation. So what I'm going to go through now is I'm going to say, okay, well, if we start from the very first number, the very first number corresponds to x is equal to 0. So I'm going to type that into the probability, or write it into that probability. Here we go. So the first number that I'm writing in is at 0.32768. The next number was at 0.4096. The next number was 0.2048. The next number on that list was 0.0512. Next number on that list was 0.0064. Oops, there we go. The next number on that list is 0.00032. Does that kind of look familiar, that very last number? That last number should look somewhat familiar because the probability of exactly 5 is that same probability. Now, look at the probability for part B. Probability for part B. Part B says probability of 2 or 3. Well, can we just come to the table here and add these two probabilities right here? If we add those two probabilities, do we get exactly this? Yes, we do. We get exactly that. Which means creating a probability distribution table is very, very important for what we have to do, because again, it's going to list out every single probability for that distribution, which means anything that the calculator is doing, we will be able to extract from this table. And if you wanted to create all of the individual probabilities, again, going down one by one, then you're going to have to do binomial PDF for the first one, binomial PDF for the second one, binomial PDF for the third, so on and so forth. You can do the binomial PDFs for all of the individual X values, and you will get those probabilities. Very time consuming. I would prefer you using the shortcut. Now let's go to part E. Part E is just going to say that we now want to create this probability distribution using our, we're going to make a bar graph out of this. The type of data that we're looking at here is discrete because we're counting students. Therefore, we need a bar graph, not a histogram. So for x is equal to 0, we go up to the probability of 0.327. So 0.327, we're going to go all the way up to there. There we are. That looks about good. Probability of 1, we're going to go up to 0.4096. So we're going to go up to 0.4096. There we are. Next one's going to go all the way up to 0.2048. 0.2048. There we are. Next one's going to go to 0.0512. 0.0512 is roughly halfway between 0 and 0.1. And the last one's 0.32. Oh, sorry, 0.0064. 0.0064, wow, that barely has a height. And then 0.00032 has definitely almost no height in accordance to what we're looking at here. All right, so this is the bar graph that I want to see. On your exam, you will have a question that says, create a probability distribution. So you will have one of these, create a probability distribution, and you're also going to have one of these where you're going to have to create that graph for the probability distribution. So make sure that pay attention to that. Now the question here says, what if we survey 200 students and I asked that the probability, what is the probability between 113 and 187 students are new? How would we find our answer then? Well, that's going to be kind of rough because 113 and 187, we don't want to make a table that large, or we don't want to keep adding probabilities continuously like that. So instead, what do? Well, instead, what we want to do is we want to use the embedded feature that we have on the calculator. That embedded feature is the binomial CDF. The binomial CDF is a cumulative probability distribution. So we want a cumulative probability distribution. Now, when we look at these cumulative probability distributions, we have to be very, very careful. And we're going to have to be very careful in the sense that when we look for this binomial PDF, the binomial PDF automatically calculates all the cumulative probabilities to the left, including the X input. This means that when we give that X input here, it's going to calculate the addition of all of the probabilities starting from that number onto the left. So if this input was, let's say, 4, then it's going to calculate the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. Right? So we have to be very, very careful with this. Now, when we're looking at these probability distributions, we're going to make sure that we start extracting all of this. All right. Now, I am not going to use this table down here. Instead, we're going to just jump straight into the examples, and we're going to be working with the examples, and I'm going to show you how my method works. So here we go. Example. A basketball player makes 75% of free throws he tries. If the player attempts 10 free throws in a game, find the probability that such and so forth. Let's see if we can extract. All right. First of all, does this meet all the requirements? All of those 4 requirements. Well, let's check the first one. Fixed number of trials. Fixed number of trials. Sure. He's doing 10 free throws. So n is equal to 10. Got it. Does he have a probability of success? Yes. That probability of success is 75% of the time he will make it. All right. So probability of success, awesome. Trials are independent. Does him making one affect him making another? No, none whatsoever. All right, which means, again, the success rate is going to remain constant. Are the trials categorized into 2 outcomes? Yes. He either makes a free throw or he doesn't. So now that we know that this satisfies a binomial distribution, let's see if we can go through and if we can start finding these outcomes. So find the probability that the player will make at most 6 free throws. That's what I want to key in on. At most 6 free throws. Now I'm going to do my work over here on the right hand side. So at most 6 free throws. Could he make 0? Yes. Could he make 1? Sure. 2? Yeah. So on and so forth. 3, 4, 5, and finally 6. Now I'm going to extend this number line just a little bit more. 7, so on and so forth. At most. This means that he cannot make any more than 6 free throws. So no more than 6 free throws. So when we want to calculate this probability, we want to make sure that this probability does not go beyond the number 6. In other words, what we're trying to calculate is we're trying to calculate this probability happening, number 6. We want this one. Could he make 5? Yeah, it still satisfies that at most. Could he make 4? Sure, still classifies as at most. Could he make 3, 2, 1, or no free throws? Yes, which means we want all of these probabilities here. So finding all of those probabilities, I'm going to say that this is going to be x is less than or equal to 6. X being any number, 0, 1, 2, 3, 4, 5, and possibly even 6. So coming here to this probability, I'm going to say the probability that x is less than or equal to 6. That translates into at most 6 free throws. Cumulative-wise, in other words, binomial cumulative, I need to know how many trials, what's the success rate, and then what number are we starting at to count to the left. That number that we're starting to count to the left is that number 6. All right. So all we need to do is calculate binomial CDF for this input. Let's go to the TI. Here's the TI. We're going to go to binomial CDF. So we want that distribution. Here we go. We want, this time it's going to be binomial CDF. That was category B. Trials. We have 10 trials. Probability of success was that point, oops, excuse me. Whoa. Point, there we go, 75. X value, the X value that we want to start at was 6. And again, it goes all the way to the left. Cumulative binomial is always starting at the number to the left. And then we press enter. We get the probability of 0.224124, so on and so forth. So that probability here is approximately 0.224. Now you can verify this. You can find all of the individual binomial probabilities for x is equal to 0, x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, x is equal to 5, and x is equal to 6. Find all of those manually using this method that we discussed here. Notice that's very, very time consuming, because now you're looking at 7 individual probabilities that you have to calculate or input. But once you find them, you're going to get that probability is 0.224, which means that binomial CDF is making our life easier. All right, let's look at part B. Part B, we want to find the probability that the player will make at least 8 free throws. So at least 8. So again, I'm going to go through and I'm going to draw my diagram again. So at least 8 free throws. That means at the very minimum, 8 free throws were made. So let's see. 8 free throws. Could he make 9? Could he make 10? Could he make 11? 12? So on and so forth? Sure. To the left, we have 7, 6, so on and so forth. All right, so we can keep going. But the probability in question is that the player will make at least 8 free throws. All right, so 8 out of the 10. Oops, my apologies. 8 out of the 10, because he only has 10 free throws, he doesn't have anything more than those 10. So my apologies. There we go. Now, remember, cumulative binomial only calculates to the left. It cannot calculate probabilities to the right. So we then have to tell it, I want to use the complement. How do we use complements though? Well, we do 1 minus whatever it is the probability that we're looking at. So the probability that we want, I will do this in blue. The probability that we want is that he makes at least 8 free throws. In other words, a minimum of 8. So minimum of 8. In the game, could he make 8? Could he make 9? Or could he make all 10? Sure. Yes, he can. Now, if we want to find that probability, and I'm going to call this that x is greater than or equal to 8, all right, or we can do it as x greater than or equal to 8. This is going to mean that I want the complement in order for me to use binomial CDF. The complement for binomial CDF is going to mean that I want everything to the left. But everything to the left, I can't include the number 8 because the number 8 is already included in this probability. So when I do the complement, I want 1 minus the probability of, and here's what we need. To the left, like Beyonce said, to the left, we want these probabilities. What probability does that start at? Well, that starts at 7, then goes down to 6, then 5, then 4, then 3, then 2, then 1, so on and so forth. Which means probability here, that x value, that is that x is less than or equal to 7. And that's what goes here. How does that look on the calculator? This is 1 minus the binomial CDF of 10, 0.75, comma, 7, because we want to start at 7. So let's go to the calculator. Here we are. So input exactly as it is. 1 minus distribution. We want binomial CDF, 10 trials, probability of success. We start at the number 7 because, again, we're trying to find the complement. So that's 1 minus the complement of this will get me that probability of the basketball player shooting or making 8, 9, and 10. We hit enter, and here's that probability. Approximately 0.526. So now that we got the probability, this is approximately 0.526. Nice. So this is the way that we're using these probabilities here, or the probability distribution for a cumulative probability, for a cumulative binomial probability. Next example. According to 2017 Washington Post article, approximately 53% of all U.S. households are wireless households, meaning no landline. In a random sample of 20 households, what is the probability that, so on and so forth? Now, feel free to do the check yourself here to see if this satisfies a binomial distribution. So take some time, come up with that conclusion. Or if you want, put pause on the video. Highly recommend that because spoiler alert's coming up. Here's a spoiler alert. It is a binomial distribution. So, we now want to extract what is n and what is p. So let's go through that. Here we go. So for this example, we're going to be running under the assumption that n is 20 because we're looking at 20 households. Probability of success stays constant at 0.53. So for this probability, we want to find what is the probability fewer than 6. So fewer than 6 are wireless only. How does that look like? All right, I'm going to need my area over here, so I'm going to erase this here. All right, perfect. Now, let's look at that. Fewer than 6. So that means I have the number 6, the number 5, the number 4, the number 3. Let's do number 7 just for kicks here. So the probability that I'm looking for. Remember, the probability for a cumulative distribution starts counting at the number that you input. We want fewer than 6, which means, do we include the 6? The answer is no, we do not include the 6. So this is not included. Which means we actually want to start our probability from 5 to 4 to 3 because, again, this is a discrete probability. So because it is a discrete probability, we actually start here and we move downward, which means x is less than or equal to 5. So how does that look like then? Well, for us, that's going to look this way, that we want the probability that x is less than or equal to 5. That means that we're looking at the binomial CDF for 20, comma, 0.53, comma, 5. Let's go to the binomial CDF function. Here we are, binomial CDF. Let's calculate this. I want binomial CDF. This time we had 20 trials. Our probability of success was 0.53. The x value that we initially want is 5, because again, we want less than 6. Hit enter, and there we have it. There's our probability, 0.0105. Awesome, so here we go. So that was a probability of 0.0105. Nice. Now the next probability. We want the probability here that more than 13 of them are wireless. So I'm going to go back to my little distribution here. All right, my number line. More than 13. So that's 13, 14, 15, 16, and then to the left that's going to be 12, 11, so on and so forth. Now, the one that I want to focus on is that I want the probability that's greater than 13. All right, so more than 13. More than 13 does not include the number 13, which means more than 13 probability-wise, I'm looking at 14, 15, and 16 that I want. However, that is a probability to the right. CDF binomial CDF only does the probabilities to the left, which means we want this probability to the left. That means that this is x is less than or equal to 13. So when we write this, we want this as 1 minus the probability that x is less than or equal to 13. In other words, this is 1 minus the binomial CDF, and then we had 20, 0.53, and then we have 13. So let's do this on the calculator really quick and see what we get. Here we go. So that was 1 minus, I want that distribution. So here we go. I want that binomial CDF, and that was going to be 20 trials. Probability of success stays the same, and that was the 13 households. Press enter, hit enter, and we get a probability of 0.09577, so on and so forth. We're going to approximate that. Here we are. That probability is now going to be approximated as 0.0958 approximately. And there we go. That's all there is to it. Now, using mean and standard deviation. Mean and standard deviation here for our examples, this is going to tell us that when we want to calculate the mean, we always use this formula, which is going to be given as n times p. To find the standard deviation, that's going to be the square root of n times p times q. So you will have to do these on the next exam, where I will give you a certain question that looks like this, and you're going to have to figure out then what is the mean and the standard deviation. So let's go through it. According to the U.S. Office of Adolescent Health, nearly 90% of adult smokers in America started smoking before turning 18 years old. Part A. If 300 adult smokers are randomly selected, how many would you expect to have started before turning 18 years old? So right here, how many would we expect? Remember that we said expected value was the same thing as an average, or the same thing as a mean, which means when we're looking at an expected value, we're really looking at a mean. If you go through, and for this example, you go through and you say, okay, well, let's see, does this follow a binomial distribution? Are all the trials independent of one another? Does the probability of success stay the same from trial to trial? Are there a fixed number of trials? Right? You're going to answer yes to all of those questions, which means this does follow a binomial distribution. So how do we calculate this expected value, or this mean? This mean is just n times p. What's n? That's 300. So out of those 300 adults, we're looking for 90% of them to be smokers. So we multiply 300 times 90. So what's 90% of 300? And that should be 270 smokers. So in a sample of 300 adults, we would roughly expect 270 smokers to have started smoking before turning 18 years old. Now the next part. Would it be unusual, in other words, significantly high or significantly low, to observe 240 smokers who started smoking before turning 18 years old in a random sample of 300 adults? So, unusually high, and then we have significantly high and significantly low. Remember, that goes back to that 5% guideline, or more specifically from chapter 2, anything that's beyond 2 standard deviations, either above or below that mean. So, in order for us to do this, we actually need a standard deviation. So I'm going to write this in green, that we need a standard deviation in order to be able to do this. Need standard deviation. All right, now my battery's running low, so I have to hurry this up. So we're going to do standard deviation is the square root of n times p times q. N was 300, p was 0.90, q, can anybody tell me what q is? Yeah, hey Mr. Castro, q is the complement of p. Yeah, awesome, yeah, that's exactly it. So q is a complement of p, which means 1 minus 0.9, the answer is 0.10. Awesome. Now, I said 0.10, but it's really just 0.1. All right, here we go. And this should be approximated to about 5.2. Awesome. So make sure you do the work. Make sure you get a 5.2. Now, what we want to do is we want to create this interval that we're going to be looking at when we want to look at what is higher or lower. In other words, significantly high and significantly low. So we have 270, and we're going to go 1 and 2 standard deviations, 1 and 2 standard deviations. Since this number is on the high part, or sorry, on the low part, then we're going to look at what it's going to be for that to see if 240 is significantly high or significantly low. So let's go ahead and fill these in really quickly. So, whoa. I don't know what that was. So 270 minus 5.2. On here, I get 264.8 minus, again, 5.2. So 5.2 again. And we get 259.6. All right, here we go. So anything to the left of this standard deviation is significantly low. Where does 240 fall in that category? So 240, where does that fall then? Oops. Technical difficulties, here we go. So 240 probably falls somewhere in here. So is it unusually high or unusually low? In other words, significantly high or significantly low? It is significantly low, according to our 2 standard deviation rule. Awesome. There it is. Nothing to it. What made this suggest about the population that was observed? So the population that was observed, again, depending on the sample size or maybe the state or maybe the population that was observed, could have maybe higher incomes, or they're more prone to, or certain communities are more prone to smoking. There's too many variables to really try to justify this here. So at this point in time, all we want to say is that that observation is significantly low with the data that is given. All right, so thanks for tuning in for section 5.2, and I'll see you all next time.